Good afternoon. This is the end video for Chapter 19, Chemistry 241, Spring of 2021. We left off with talking about reactions and that we can do with ketones. This can also be done with aldehydes, where we react with the carbonyl-containing compound, two molecules of an alcohol. It can be done with the aldehyde. It gives us an aldehyde, an acetal. If we do it from a carbonyl-containing compound, these are called ketals. Again, reaction mechanism. C double bond O. The oxygen is protonated, creating an electron deficient carbon. Nucleophile comes in, breaks the carbon-oxygen double bond. Water can come in, pick off a hydrogen, giving you this corresponding hemiacetal, an OH and an OR. Protonation of your water, protonation of your OH to give you a masked water molecule, kick down of the electron pair, the carbon-oxygen bond breaks, giving you this intermediate. An alcohol can come in again, break the carbon-oxygen double bond, loss of a hydrogen to get you either to the acetal or the ketal, depending upon what you started with. One of the uses that you can have with these kinds of groups, these acetals or ketals, you can choose to mask the presence of a carbonyl compound, such that if you're needing to do any other chemistry that would potentially destroy your ketone, if you can mask it, create something else out of it that is not sensitive to the reaction conditions, then you can do your chemistry that you're wanting, and then at a subsequent time, recover your C double bond O. One of the easiest processes that you can use is reacting this ketone with a diol, a 1,2-diol, to give you this 5-membered acetal intermediate. You can then react the acetal protected intermediate with a reducing agent. The carbonyl would be attacked by your lithium aluminum hydride. It would reduce it to an alcohol, but since it's masked, you only have the ester here. So the ester is reduced down to the corresponding alcohol. Under acidic conditions, you cleave the protecting group to give you your CO back. So with hydride reduction sources, you can't go directly from the aldehyde to this, you can't go from the ester to the aldehyde without also destroying your carbonyl. So if you protect it as this cyclic acetal, then you can undergo the reduction reaction of your ester to your alcohol, reclaim your C double bond O under acidic conditions, and you've essentially done chemistry only at the ester, but leaving this carbonyl in place. So how can we change 2-pentanone with 1,3-propane diol? So here we have 2-pentanone. We're reacting it with this 1,2,3 diol, 3-carbon containing diol with 1,3-propane diol. So here's 2-pentanone. This oxygen ends up being bonded to the carbon of your carbonyl, and that oxygen ends up being bonded to the carbon of your carbonyl, giving you the 6-membered intermediate. If you have any other functional group that's present in your molecule, you can do chemistry there and not touch that cyclic acetal system, because the chemistry is not able to occur there, so you can do other reactions depending upon what you have in your molecule. One of the most valuable reactions is the Wittig reaction. And get my notes up to speed. can start with an aldehyde or a ketone, react it with a phosphorus-containing intermediate. This carbanion charge is stabilized by the presence of the positive charge on the phosphorus immediately bonded to it. It acts as a nucleophile, creating and adding to this C double bond O to give you this kind of intermediate. Because this is now a carbon-carbon bond, here is the carbon that was originally the carbanion. There is the carbon of your carbonyl. This is now a single bond. There is bond rotation that can occur about this carbon-carbon bond, such that the R2 rotates around and the oxygen is brought into position where the hydrogen was. You have this oxygen next to this positively charged phosphorus. It can then form this four-membered intermediate, what's called a betaine, and you eliminate triphenylphosphine oxide and the corresponding alkene. So essentially, from this carbonyl, you can add another huge piece of carbon network, just depending upon what R1 is. You can add it to the C double bond O, giving you this corresponding alkene. You can form this initial Wittig reagent via any number of synthetic pathways. I will mention just a couple, but the variability that you have here is quite extraordinary. R1 can be just about anything. R2, and if this is the ketone, what can be here can be just about anything. This is an extraordinarily powerful synthetic tool. Triphenylphosphine is a good nucleophile in SN2 kinds of reactions. So we have this triphenylphosphine. It has this lone pair of electrons. It can do an SN2 displacement of a halogen from a primary alkyl halide. You get the phenylphosphonium bromide. Turns out that the hydrogens here are extraordinarily acidic. You hit this, or you react it with a strong base, like butyllithium, you get the neutral charged phosphorane intermediate. What ends up being transferred to the ketone or aldehyde is this group right there. The one limitation, you cannot use this reaction sequence to prepare tetrasubstituted alkenes due to the congested stereocenter, the congested site of attack of this carbanion on your carbonyl-containing compounds. Start out here with your electron-deficient carbon. First, nucleophilic attack of this carbanion to the electron-deficient carbon of your carbonyl-containing compound. This is considered an ylide. You form a carbon-carbon bond. Free bond rotation about that carbon-carbon bond can bring the oxygen in close spatial proximity to your positively charged phosphorus. This minus charge then forms a bond with your phosphorus, giving a neutral charged betaine intermediate. That's this four-membered carbon-carbon oxygen phosphorus species. That's called a betaine. This spontaneously eliminates the triphenylphosphine oxide and gives you the double bond. You can use triphenylphosphine oxide, the triphenylphosphine derivatives to end up creating you the double bond, where in other ways you would get mixtures of products. So let's say we're wanting to create an exo double bond outside of the ring. We want to create the species. Well, we can do it one of two ways. We're wanting basically to cause an elimination reaction to happen. Well, if we start with this ketone and we add phenylmagnesium bromide, we initially create the corresponding alcohol. Then if we hit it with a dehydrating agent like trichlorophosphine, we could get the double bond elimination. Problem is we have two sites that we could eliminate from. We have double bond, we have hydrogens on adjacent carbons here and there. They could eliminate to give you the double bond, or we could lose hydrogens here on this methyl group that's outside of the ring. We get primarily the tri-substituted double bond. This is a di-substituted. So the double bond inside the ring is favored due to forming the more substituted alkene. We do get some of this exo double bond, but we don't get enough. We don't get a lot of it. However, we can use to create the alkene the Wittig reaction. The triphenylphosphine ylide gives us the CH2 attached to the carbon where the double bond O is, so it gives us this exomethylene in relatively decent yields, 84%. So working and thinking about how we could use carbonyl-containing compounds and ylide reactions to create synthetic transformations. What carbonyl-containing compounds and phosphorus ylides must be used to prepare these guys? Well, this first material, A, we can either have double bond there, or we could flip there and have that derivative. If we use this compound, we would get the carbon-carbon bond forming there, and then the double bond would form between these two carbons, losing the phosphorus triphenylphosphine oxide, creating the double bond and the CH3 group. Or we could flip and have the aldehyde here. You would have the double bond going to, let me see, that ylide and that aldehyde, giving us the double bond and the CH3. So we're looking at forming the carbon-carbon double bond there. That would either mean we have a C double bond O here or a C double bond O here. Using the Wittig reaction, we would have to have the C double bond O here, either acetone or this corresponding aldehyde, this benzaldehyde, just depending upon how you wanted to break it. So for the first reaction, we break the bond here. If we have the C double bond O here, we have to have this 2-carbon fragment as from our ylide. This carbon ends up being bonded to there for the single bond. When you lose the phosphine oxide, you form a double bond between this carbon and that carbon with your CH3. B, you can either use the C double bond O acetone here or benzaldehyde. Here you can choose using acetone and this phenyl substituted derivative, creating this ylide. This then condenses with the C double bond O, giving you your tri-substituted alkene. Other reactions that aldehydes and ketones can be induced to undergo that have synthetic transformation value. A reaction is the Cannizzaro reaction. It takes place when you have an aldehyde, primarily an aromatic aldehyde, in strongly basic conditions. Again, here we're looking at basically pelletized KOH pellets rolling around the bottom of this flask where you have your benzaldehyde. So you have the nucleophilic addition of OH minus to your carbonyl compound. When this electron pair, non-bonding pair, kicks back down, it produces a hydride minus anion as the leaving group. This hydride can then attack another carbonyl containing molecule and reduce it down to the corresponding alcohol. This can have some use, but it is specifically limited to aromatic containing species. So if we have phthalate, it's treated with strong base, basically pelletized KOH. The O, hydroxymethyl benzoic acid, is formed. So if we're interested in figuring out how this transformation was achieved, here we have our phthalic aldehyde. Nucleophilic attack of the oxygen on the electrophilic carbon breaks the carbon-oxygen double bond. Notice this C double bond O is in correct spatial position such that this can be an internal hydride transfer reaction. This doesn't have to bump into anything else. It can happen as soon as this intermediate is formed. This C double bond O, this electron deficient carbon, is spatially and extraordinarily close spatial proximity, such that this hydride adds to the carbon double bond, getting us to the corresponding benzoic acid and the corresponding alcohol. Protonation of your alcohol followed by protonation of your acid gets you to the corresponding oxidized carboxylic acid, but reduced aldehyde to give you the corresponding alcohol. So step one is the addition of the OH into the C double bond O, getting you to this tetrahedral intermediate. In a second step, you let go, or hydride leaves can add to the adjacent C double bond O. This forms a carboxylic acid. This forms the corresponding tetrahedral species that will eventually become your alcohol. Third step, your OH, the O minus picks up a hydrogen. Fourth step, protonation of your carboxylic your carboxylate forming the carboxylic acid. One of the next most important reactions besides the Diels-Alder and the Illard-Urbidic reaction is conjugate nucleophilic addition to alpha beta unsaturated aldehydes and ketones. We have two ways that this reaction can happen. We have what's known as 1,2 addition. We've talked about this a little bit. This carbon is electron deficient. That oxygen is electron rich. This oxygen is screaming out for a pair of electrons. It is a nucleophile. It is an electrophile. The nucleophile having a minus charge or an unshared pair of electrons can come in, break the carbon-oxygen double bond, give you this tetrahedral intermediate. You can pick up a hydrogen to give you the corresponding alcohol. Or, depending upon the structure, we can have what's known as conjugate addition or 1,4 addition. Here, the reaction happens at the carbon of the carbonyl. Here, the reaction happens on adjacent carbons to your carbonyl. Notice we do not have a double bond specified here. Here, we have a double bond that is alpha, one position away from the C double bond O. So here we have addition of a nucleophile to the carbon-carbon double bond of the alpha-beta unsaturated aldehyde or ketone. Remember, these systems are all conjugated. Nucleophile can come in, the electron pair flips, can create the carbon-carbon double bond. This electron pair of your oxygen between the double bond electron pair flips up to give you this oxyanion. This can kick back down. The electron pair there can pick up a hydrogen to give you your substituted saturated aldehyde or ketone. Or the nucleophile could attack. You get placing of the carbanion or the electron pair on that carbon itself, giving you what's known as the enolate anion. This could pick up an H plus and get you to the same point. So you can have either direct 1,2 addition or what we know as conjugate 1,4 addition. So 1, 2, 3, 4. For conjugate addition, conjugate 1,4 addition, you have to have a double bond immediately next to the C double bond O of a carbonyl. For 1,2 addition, all you need is the carbonyl. You can use any number of nucleophiles to undergo either 1,2 direct addition or 1,4 conjugate addition. You could use amines as the nucleophile. You have this alpha beta unsaturated ketone. C double bond O. This carbon is directly bonded to the carbonyl, so this is an alpha beta unsaturated carbonyl containing compound. Primary or secondary amines add to alpha beta unsaturated aldehydes or ketones to give you beta aminoaldehydes and ketones. So the electron pairing your nitrogen attacks here. This double bond flips up there. The electrons go up there to give you this intermediate species. This has a hydrogen that can be lost and eventually is lost to get you to the amino ketone, reclaiming your C double bond O. This primary and secondary amines do not undergo 1,2 direct addition. This would give you the corresponding imine, but we don't get that. We get almost exclusively conjugate 1,4 addition. We can add water in a 1,4 addition. So here's the alpha, there's the beta. We can add 1,4 water to an alpha beta unsaturated aldehyde ketone. So this adds to this beta position. Electrons kick up there, this kicks up here, gives us this hydroxy compound. The position of this is generally an equilibrium reaction. Generally, this is one of the reactions that can happen in the body, and it plays a very important role in the metabolic processes in the human system. The position of the equilibrium generally favors the unsaturated reactant. So here we start with with a cis aconitate, but with the addition of the OH, it gets to isocitrate. This is a very common intermediate in biosynthetic pathways. It's a way that the OH group can be added in, and then the C double bond O kicks back down, displaces the water or the OH minus in biological pathways. Other reagents that add exclusively 1,4 are organocopper reagents or Gilman reagents. So we can have an alpha beta unsaturated ketone and react it with a lithium diorganocopper reagent. The diorganocopper reagent are formed by the reaction of copper iodide with an organolithium derivative. We form what is known as a Gilman reagent, or a diorganocopper species. Basically, this forms a organocopper reagent is basically a source of the carbanion that you have as your organolithium reagent. So materials that can undergo 1,4 reaction: primary, secondary, tertiary, alkyl, aryl, and alkenyl groups all can form these organocuprate reagents. Those that have carbon-carbon triple bonds in there don't readily form the Gilman reagents, but primary, secondary, tertiary alkyl groups, aromatic groups, and double bonds can easily react to form these organocuprates. So if we react this C double bond O, this alpha beta unsaturated C bond O, with a Grignard reagent, you get 1,2 addition only. The reaction works nicely, 95%, but if you want to add a carbon-containing group to this position, you have to use the organocuprates. This reaction adds the methyl group in and gives you a nice yielded product, 97%. If we look at the reaction mechanism, conjugate nucleophilic addition of the diorganocopper reagent, R2Cu minus to a ketone. The lithium complexes with the oxygen. The carbanion adds in, double bond breaks and goes here, oxygen goes there. You get a transfer of one of the R groups to your carbon, you lose an organomonocuparate. So one of these R groups, since they're identical, gets transferred to your formerly alpha beta unsaturated compound. Last up in the acidic workup, ketone flips down, or the electrons here flip down to give you the carbonyl. The bond that breaks here picks up a hydrogen to give you the substituted product. So how could we use a conjugate addition reaction of a lithium diorganocopper reagent to make that compound? Remember, we're looking to add this group to the aromatic ring. If we use a diorganocopper reagent, it does not touch the carbon of your C double bond O. Start out with this alkene, react it with that species. So we have a lithium complex to the CH2 double bond CH to copper. We have two of these. This adds this aromatic, this double bonded material to that ring junction. It adds 1, 2, 3, 4. So 1 it adds right there, 2, 3, 4, giving you your final product. Real quick, let's look back and familiarize ourselves with some spectroscopy. Again, aldehyde, 1700 wave numbers for your C double bond O. You have the aldehyde fangs at about 2750, 2850. Aromatic ring, here's 3000. Nothing immediately to the right of 3000, but something to the left of your aromatic hydrogens. Your ketone, again about 1700. Cyclohexanone, there's something, there's 3000. Anything immediately to the left? No. But we do have stuff immediately to the right. All sp3 hybridized carbon. This says C double bond O, cyclohexanone. Different regions of where aldehydes and ketones absorb, just depending upon what kind of environment it is. Saturated aldehyde about 1730, aromatic aldehyde about 1705, alpha beta unsaturated aldehyde 1705, ketones generally on the upper region of your in about 1750, cyclopentanone, cyclobutanone, aromatic ketone 1690, alpha beta unsaturated ketone about 1685. So where would you expect to find of the IR in each of these compounds? 4-pentene 2-one and 3-pentene 2-one. So here we have a C double bond O. Is it conjugated to this double bond? No, it's not. So it will appear above 1700. It's not an alpha beta unsaturated ketone. But this guy, this double bond is immediately adjacent to the C double bond O of this ketone. Therefore, this is a conjugated, this is an alpha beta unsaturated ketone. It absorbs below 1700, about 1685. Proton NMR, something above 9, but below 10 is an aldehyde. Carboxylic acids are coming up at 12. Here we have acetaldehyde, Hydrogen in red here is split into a quartet. N plus 1, we have 3 non-equivalent neighbors, so it's split into a quartet. Here we have the CH3 of this acetaldehyde. It's split into a doublet. We have 1 magnetically non-equivalent neighbor, N plus 1. If N is 1, 1 plus 1 is 2, so the hydrogens here are split into a doublet. So the aldehyde between 9 and 10. Anything above 10, you're looking at a carboxylic acid. Carbon 13, NMR. Generally, your C double bondos are somewhere about 190 to 215. There are no other carbons that appear in this range unless they're a carbonyl. Saturated aldehydes or ketones absorb above 200. So acetaldehyde 200. This is an aromatic aldehyde. It's conjugated to the double bond, 192. Butane to butanone, non-conjugated, above 200. Again, cyclohexanone, carbonyl above 100. Acetophenone, carbonyl, since it's conjugated to the aromatic ring, it's below 200, about 198. Looking at mass spectroscopy of these guys, we can have the McLafferty rearrangement. Excuse me, let me turn my phone off. Aliphatic aldehydes and ketones that have hydrogens that are on the alpha, beta, gamma, 3 carbons away from the C double bond O can undergo what's known as the McLafferty rearrangements. To give you the beta gamma alkene and the corresponding carbonyl containing compound. Other things that these carbonyl containing compounds can do, they can undergo alpha cleavage. Again, the atom that is part of the carbonyl, those things that are directly bonded to the carbon of the carbonyl can break in a radical fashion to give you those stabilized cations. So here we have the fragmentation pattern of 5-methyl-2-hexanone. So here's 5-methyl-2-hexanone. 1, 2, 3, 4, 5, 6. So the carbonyl is at C2. We got a methyl group at C5. So 5-methyl-2-hexanone. Apparent molecular weight's 114. So that's this peak right there. If we undergo alpha cleavage, right there, breaks in a radical fashion. We can get this corresponding radical cation. And that stabilize that radical right there. Or this can be in the right configuration where it can do the McLafferty rearrangement, and we end up with a double bond between here and there, between this carbon and that carbon, giving us this alkene and this stabilized intermediate, giving us the mass at 58, the mass at 58 and the mass at 43 for this alpha cleavage product. That's chapter 19. What we will do when we start back on Monday the 12th is we will have a day of review. I will try and dredge up an old exam that I can post and that we can work through to get your mind back up to speed with material covered on this next hour exam. Have a good break. See you when you come back.